resonance spectroscopy, NMR. Principles including spin energy levels and applications of proton and carbon-13 NMR, excluding features of instrumentation, right? So it's all that looking at the graph and making sense of it. Analysis of carbon-13 NMR and use of chemical shifts to determine the number and nature of different carbon environments in a simple organic compound. And analysis of high-resolution proton NMR to determine the structure of a simple organic compound using chemical shifts, areas under the peak and peak splitting patterns, excluding coupling constants, and application of the N+1 rule. Right, so we've got an N-1 rule in chem and an N+1 rule in chem. Don't get them mixed up, right? N-1 relates to how many waters are produced in condensation polymerization, right? N+1 only refers to the splitting pattern of high-resolution proton NMR. Right, two types of NMR. One is called proton NMR, one is called carbon-13 NMR. They tell us two things, right? The number of peaks in both NMRs tell us the number of different environments, right? The position of the peak tells us the nature of that environment. So the number of peaks tells us the number of unique environments. Its position on the spectrum tells us the nature. Notice how it's carbon-13 NMR, not carbon-12. Okay, so the principles must have odd-numbered nuclei in order to cause what's called a nuclear spin, right? So we're using radio waves and essentially using radio waves, and it's causing spins within the nuclei. It's about all you need to know, right? Using radio waves. So within the nuclei causes spin to occur using radio waves. Just think about it that. We won't go into too much more detail than that. So IR, right, relates to vibration of bonds. NMR, radio waves, changes the spin. We use this thing called TMS, tetra, meaning 4, methyl, we know what a methyl group is, silane. So we know what methane is, right? So methane, CH4, silane replaces the carbon at the center with a silicon atom instead. Silicon, right, group 4 element. Tetra meaning 4 methyl groups coming off that silicon, right? One of the reasons for using this as the standard is we have 4 identical carbons, yeah? Because, all right, close your eyes for a moment. Open your eyes. Did you realize I rotated that image around? Yeah? You didn't even close your eyes. Okay, all right. Right, I rotated the image around in 3-dimensional space. Yeah? Every carbon is chemically and physically identical. Similarly, we've got 12 hydrogens here, all chemically identical. So we can't tell one from the other. So how they're going to interact with one another means that they're all going to interact the same, and we end up with a singlet, one single peak. Yeah? And so what we're looking at is we have this in conjunction with our compound, sample of a compound that we put into our NMR, right, with this, and we're looking at how the different hydrogen and carbon environments kind of interact or shift away from these. Yeah. Environment like CH3 is an environment. CH2 is a different environment. Carboxylic acid, COOH, is another environment. Yeah? Does that make sense? So we've got many different classrooms in this school that are all timetabled. This is one environment. Your physics class is a different environment. Yeah?
These environments all have to be something to do with the carbon.
Yeah. Well, in carbon, NMR, it has to do with carbon. In proton NMR, it has to do with the different hydrogen environments.
Can we look at the different NMRs? Or?
Yes. Both carbon and proton NMR. NMR spectra, i.e. a graph, is a two-dimensional graph, chemical shifts in parts per million. I'm not worried about the units, right? With NMR, I'm after how we analyze it. So if I look at this compound here, right, 1,3-dichloropropane. It's a bit of a complex example to look at, but I've got two peaks, right? Because I've got two different carbon environments because there's symmetry, right? I've got two unique carbon environments and I've got two unique hydrogen environments because of the symmetry. We'll look at more simple examples to start with. It's just an example of, so we'll come back to this example. Not concerned about the instrumentation, so I'm going to skip over that. Right, this thing about chemical shift. Like with IR, notice how the graph of the horizontal axis goes backwards. Start at 0 on the right-hand side, and then it goes up. So, as we increase this way, we refer to it as downfield. Higher frequency, don't worry too much about de-shielding, right? Lower frequency is more shielded. Don't worry too much about shielding. Yeah, so just think about it, downfield or upfield. Upfield, closer to 0, downfield, 10 or plus more. Nuclei resonate to a wide range to the left or more rare to the right of the internal standard TMS. So we would expect that a methyl environment, a CH3 environment, would be pretty close to TMS. Make sense? Because the environment is very similar, right? Whereas a carboxylic acid, carboxyl group, is about as far away from looking like a methyl group. Yeah? Okay. Carbon-13 NMR. The number of peaks tells us the number of unique carbon environments. So we've got to be mindful of symmetry. Yeah? So if we're looking at our mass spec and we see that nice peak, it's halfway of the parent molecular ion, we know there's symmetry there. Right? We're going to have two types of symmetry. One is bond symmetry, right? So if I say butane has a central bond symmetry. I can cut it into two CH2CH3 groups. Does that make sense? Yeah? If I look at propane, has a central atom symmetry, where the symmetry goes through the atom. Yeah? Make sense? Ish? Right. So, get out your best friends. Won't look at too many functional groups yet. We'll look at some simple examples to start with. And notice you've got two tables. One goes over 2 pages. Central bond symmetry, where the symmetry is through a bond, and atom symmetry, where the symmetry lines through an atom. We're looking at how the carbons interact with each other. It's a really great website called compoundchem.com. An ex-chemistry teacher that I don't know decided to break out in form of these really useful infographics. It helps to understand. Maybe I'll print this off for you. All right. I won't start with ethanol. I'm going to start on the board. Let's grab a whiteboard and look at some simpler examples to start with. Okay, so let's look at, say, propane to start with. So carbon 13 NMR. Let's look at, let's say propane. Okay, propane, we notice we've got symmetry down the middle. So we have a CH3 environment and a CH2 environment. At 0 parts per million, or delta in parts per million, at 0 is where our TMS is. Looking at my, back to here, notice an RCH3 on carbon 13 appears somewhere between 8 and 25. So here's, say, 25, 50, 75, 100, etc. So I'm expecting a peak to occur here-ish, or somewhere between there. An RCH2R, so this second environment, has a chemical shift between 20 and 45. So we're expecting a second peak there, right? So this peak here corresponds to CH2, and this corresponds to our CH3. Does that make sense how that looks? Yeah? All right, let's consider let's look at, did I say propanol? Let's look at propanol. How might that be different? So propan 1-ol. Propan 1-ol, we notice, does not have symmetry. Yeah? So given that propan 1-ol does not have symmetry, we expect there to be 3 different carbon environments. We've got a CH3, CH2, and a CHOH environment. Yeah? 3 unique carbon environments. There's my 25. I've got a CH3, so I'm expecting something there. I've got a CH2, so something there. And now my CH2OH occurs somewhere between 50 and 90. Right? Here's my laser pointer. Right? So there's my alcohol, CH2OH. So somewhere between 50 and 90. So there's my CH3, there's my CH2, and there's my CH2OH. Something like that. If I look at propan 2-ol, however, I have symmetry. I have symmetry through that central atom. So I only have two unique environments.